Okay, so last time we were talking about surface integrals, right? We talked about scalar surface integrals, and we also talked about vector surface integrals. Pretty weird concept, but it was motivated, of course, by a natural question we encountered back in Chapter 3. Namely, I want to know how much fluid is passing through a surface if that fluid is represented by a vector field. And, a lot to say about that, but of course our Chapter 3 treatment made assumptions that that are not real world plausible, right? That all surfaces are flat and all vector fields are constant. That's not how it works. So we entertained the question of non-constant vector fields on curved surfaces, and as one does in a calculus class, chop it up, add it up. Right? I mean, this is what integrals kind of fundamentally are, really. And so we chop it into little pieces, and then on each little piece, we recover kind of the old simple story, right? That it is approximately flat. And it's such a small piece that the vector field is approximately constant. And so we can use our old formula for flux from Chapter 3 as applied, as an approximation, errors going away in the limit, as an approximation on each little piece, and then we add up those pieces like this, thus giving us this new construction that is really fundamentally different from a scalar surface integral. And so let me remind you, this is what I'll say is my preferred notation. The idea being that we want to recognize what comes from the domain, right? This ds here tells you about the domain. It's telling you how big is that little piece of the domain and how is that little piece of the domain oriented, right? It's telling you size ds and orientation little n. And then, to be distinguished from the external thing independent of the surface, namely the vector field in this case. Right? So breaking it down like this, you can really see more explicitly that, this is really a very fundamentally different kind of critter from a scalar surface integral. And so that's the term vector surface integral. Okay, so that was all last time. And let's see here. Then I guess we did we talked about how to do computations, and roughly the big idea is we already know how to compute everything that's written down here. Specifically, ds, right, is magnitude of capital N times ds dt, and then we make the seemingly innocent observation that those two things are equal. There's my confession to the math crime right there. I'm not saying exactly what the crime is just yet. We'll get to that. But anyway, that said, full confession to come later. Here is a parametrized formula that you can compute knowing only your parameterization, right? Out of which you get the n vector, and which you then plug into your capital F vector. And so from a parameterization, you can compute flux with this formula here. Okay, all right. And I guess we did the example last time, and this is where we left off. So vector field, surface. Step 1: parameterize your surface. Right? If you're going to pull back through a parameterization, very first thing you need is that parameterization. Right? So you parameterize, then you take the appropriate derivatives, compute the appropriate cross product. Right? I'm skipping over a bunch of algebra here, right? Again, this is stuff that y'all, should be able to do. And then you don't even have to take a magnitude, right? This capital N vector is the thing that you dot the vector field with, and you get a single variable integral, and off you go. Okay, so that's where we left it off last time. So dangling, right? What do they call it? Cliffhanger. What was the crime? What was wrong with this? Right? I mean, isn't it true that if it looks like a duck and quacks like a duck, doesn't that make it a duck? Right? This vector here, this product, has the same magnitude as capital N. It points perpendicular to the surface, just like capital N. Isn't it capital N? So here's the little bit of a crime. It is true that this point's perpendicular to the surface. It is also true that this point's perpendicular to the surface. That doesn't mean they point the same direction. There are two directions that are perpendicular to the surface, not just one. Right? So that's the little subtle math crime that I committed. So let's ask, do we have to worry about the choice of parameterization? Does it matter how I parameterize the surface? So specifically to the concern that I just brought up, right? The orientation that's defined for the surface, keep in mind, is an indication of which of these two possible directions through the surface are we interested in. Right, which one of these defines the positive direction through the surface? And then I have to compare that with the parameterized normal. And keep in mind, when you write a parameterization, that parameterization gives you these partials, which then gives you explicitly a capital N vector, right? This capital N vector has never heard of the what the question asked in terms of which direction is the positive direction through the surface. The parameterization just says, oh, you've defined me as a parameterization, boom, boom, capital N vector comes directly out of the formula for your parameterization. So the looming question then is these two orientations. Oh, and I'm just going to look at the unit vector for comparison purposes. I've got two unit vectors. One comes from the orientation. One is defined in the statement of the question. The other one is, I'm going to say, kind of an arbitrary orientation that comes from I'm going to say, arbitrary choice of how we parameterized. And again, there's lots of parameterizations. There's no canonical parameterization. You can make up lots of different parameterizations. Right? So the big question, are they the same? And it could go either way, right? I mean, if the question here was, let's talk about flux downward through this surface, well, that's downward through the surface. The parameterization orientation, though, is upward. Those are different. And in a case like this, where again the green orientation, given orientation of the surface is downward, but I parameterized with an orientation that ended up being upward, they're not the same. And this business up here would be wrong in that case. Everybody see what I'm talking about? Right, and I've got that kind of fleshed out a little further down here. Here's that same equation that we had. Let's see, I'll get the color coding in here. This vector, little n here, that comes from the definition of flux. That comes from the given orientation of the surface, and so anyway, that's the given one. But what I'm claiming that this product equals, right? Claiming that equals to that. This comes from a direction that independently comes from the parameterization, and green is just not equal to blue in this case. Pausing. I want to make sure everybody's comfortable with the concern that we have here. Everybody happy with everybody see the issue, the independence of these two orientations, and one of them was required in the statement of the question, and the other one's an arbitrary one that we made up, and we just don't have the right to just decide, well, I'm going to parameterize this certain way, and well, I guess I'm going upward. Or you just can't. The question says, in this case, downward. Yes.
Aren't they just like anti-parallel to each other?
Oh yeah. No, this that's right. This is not going to be a uncircumventable problem. That's right. But I just right now I'm focusing on the fact that it is a problem, and you're right. It's going to be an easy fix. Yeah. Absolutely. Okay. Now, of course, let's recognize there is also the possibility that it could be that maybe the question is stated in such a way that the orientation happens to be in exactly the same direction as the parameterized unit normal. In which case, fine, absolutely, no problem. We got lucky. These things then are equal, and we're all good. We got lucky. It was a coin flip. We called it right, and not a problem. So that's the thing. We've got this kind of a coin flip. When you write down a parameterization, you are making an arbitrary choice that 50-50 might be right, might be wrong. Okay. All right. So that was the problem up here. That's why these might not be the same. And I kind of swept that under the rug initially because, again, we had a new formula. I wanted to let's take it out for a test drive. Let's actually do one, get a win under our belts before we deal with this more subtle issue here. Okay, so in practice, how are we going to deal with this? Well, step one, don't worry about it. When you write down a parameterization, it's very hard at the outset, as you're writing down your parameterization, to tell which direction you've parameterized, because you just can't see it from the formula here. Like here's a parameterization. Is this upward or downward? From just at a glance from the formula, as I write this down, I haven't got the slightest. I can't tell. Right? It just doesn't leap off the page at you. So step one, don't worry about it. Step two, look later and check it out, and just take a glance. Look at your parameterized normal, and see if it's pointing in the correct direction. If it is, great. If it's not, then exactly as you've said, you're off by exactly a minus sign in every term in that integral. And if you're off by exactly a minus sign, then yeah, you're fine. Just multiply by -1 and keep on trucking. Does that make sense to everybody? Okay. All right, a little bit of good news before we go on and do an example. As long as your parameterization has this correct orientation, as long as you've considered the possibility that you might have oriented it backwards, upside down, inside out, however you want to say it, other than that, parameterizations don't matter. Right? So you don't have to worry about whether you have the infinitely many possibilities. You don't have to worry about whether you got the right one. They all do the same as long as you have the orientation correct. Okay, so let's get our fingers dirty now. And here we go. So now you'll recognize this question. This looks a lot like the first example that we did at the start of, that I reviewed, that technically we did last time, reviewed at the start of today's lecture. I got the same vector field, still want to compute the flux, same surface, everything's the same, except now the statement of this question says I want the downward flux. So downward through this surface is the correct direction. By contrast, again, here was the original example. In the original example, it was upward. So that's the only difference, right? New question, how are we going to deal with the fact that this is a downward flux? What we're going to do, as I said before, is step one, don't worry about it. Parameterize however you like. It doesn't matter. Just any parameterization. This is a graph. I like graphs. I'm going to use the graph parameterization. Boom. And then proceed. Take your partials, take your cross product. Now you've got your capital N vector. Here's where you have to stop and pause. Here's where you have to say, okay, now that I know what my capital N vector is, going back up to this picture, I know what direction my parameterization is pointing now. And I have to then compare that with, which direction is my surface oriented as by definition, and then I've got to compare. Okay, so looking back down to here, let's see here. Well, I was supposed to parameterize downward. Did I? No. I've got a positive third component. That means that this is, obviously it's not pointing exactly straight up, but it's pointing, if you were going to call vectors like this that are, always at least somewhat up, right? That orientation, you couldn't possibly call this downward. If you're going to call this anything, you'd call it upward. We'll come back and talk about the terminology in a minute here. But why did I color that orange? That's my... Yeah. So these are the things I'm comparing. So, did I orient it correctly? Nope. Right? Those are different. Supposed to do it downward, ended up accidentally doing it upward. And so, do we have to start all over, throw out that parameterization, get a brand new one, hope for the best on the second one? No, just don't worry about it. Just say, whoops, I oriented this backwards. We insert a minus sign by way of apology, a restitution for having done it the wrong way, and proceed. Everything's fine. That's all you need. Just identify whether you did it right or wrong, and if necessary, fix it with a minus sign. Everything else is good. Okay. All right. What do you think? Any questions? Everybody's happy? All right, now I do want to talk a little bit about where to put in the minus sign. We were asked to compute flux. The flux was defined by the statement of the question. There's nothing wrong with this being phi. That needs to remain phi. That's what you were asked. Flux is defined as this formula. The orientation of the surface is built in to the ds vector. So this is always equal to this. These are the same, right? Where the minus sign comes in is where my wrong parameterization shows up. That's where you need to fix the minus sign, right? So this thing right here, when I write double integral f dot capital N dsdt, this capital N, that's the thing that's wrong. That's the thing that I parameterized backwards, right? So I was interested in computing flux based on the given orientation. It's when I introduce the parameterization that my mistake comes up, and so the minus sign goes there. Right, it goes in between when you were right and when you effectively wrote it backwards. Does that make sense to everybody? Now, I emphasize what you can't do. Right, what you can't do is write this and then this and then leave it off here. If you were to just leave it off there and just claim that that's equal to this, and then subsequently realize, oh shoot, you know what? This thing here. This thing here. Oh gosh, I think I'm backwards, and then just arbitrarily introduce the minus sign here. That doesn't work. It doesn't make sense. You're saying then that these two things are equal, right? You're saying, let's see, just to get it on the screen here. You're claiming that these two things are equal. They aren't. These two things are not equal. So that's a sign error. That's a mistake. Does everybody see that? Right? Furthermore, you're also saying, if you do this, there we go. You're also saying that these two things are equal, or said differently, that these two things are opposites of each other. No, they're not. Right? That's wrong too. So this is a situation where if you're not careful about where you put it, you end up with, in fact, two canceling sign errors. And again, I remind you, it's not about the answer at the bottom of the page. Well, yes, of course, it's going to give you the same answer at the bottom of the page. That's not what this class is about. What you have is two canceling sign errors in your reasoning. The reasoning is what matters. So be careful about that. Make sure that you think through where does the sign go, and then yeah, that's all there is to it. Okay. Everybody happy? All right. Okay, let's talk about the language a little bit. This is awkward. When we talk about an orientation, it's just a hard thing to talk about. If you think about it, an orientation actually is, for example, it's a collect. I better switch into pencil mode here. An orientation is a whole collection of vectors, most of which are different. Right? So if I wanted to talk about this orientation, this blue orientation for this surface, oh my, it'd be a lot of trouble for me to do the algebra to figure out exactly the formula for all of these vectors as depending on how they depend on position there. I don't want to have to write all that down just so for conversational purposes to describe, which orientation I'm talking about. Of course, there's this other orientation here. This is sort of the other alternative. And when you have only two options, it's pretty nice to have convenient, speaker-friendly ways to distinguish between those merely two options. So in a case like this where your surface is this paraboloid that I've got here, sure, you could write down explicit formulas. My gosh, that's a lot of trouble. Practically always, people are not going to do that. What they're going to say is, look, these are clearly different orientations, and I'm going to choose language that it's not going to be right, it's not going to be exact, it's not going to be precise, but it will unambiguously distinguish between the two possibilities. Right? So a great way to do this is to use the language of upward and downward. Right? So this orange orientation, most of the vectors aren't exactly straight up, but they're all somewhat up. And the alternative blue orientation, none of those vectors are in any sense up. So upward, pretty unambiguous what that means. And then likewise downward, analogously, unambiguous, right? If I say downward, which do you think I mean, orange or blue when I say downward, right? No question, clearly we mean the blue one. Does that make sense to everybody? So heads up with the language, right? The choice of language won't always be a precise algebraic description of exactly what the orientation vectors are. It'll be an unambiguous, sloppy description of what those vectors are. But it is important that they be unambiguous. So, for example, now a lot of people might look at this and say, okay, well, the orange vectors are all pointing kind of inward, if you will, and the blue vectors are pointing kind of outward. That's, I get it, right? I think most people would look at the blue and the orange and would interpret what you meant by that, but I feel it necessary to point out there is actually no inside. Right? There is no inside. This is not a closed surface. This is a cereal bowl. Right? It's open. So inward versus outward, technically not defined, and if one wanted to be obstinate about it, you could claim, I don't know what you mean. Right? So this kind of language, I would say, veer away from that in a case like this because it's only mostly unambiguous. Now, by contrast, in this case, if you had this surface, inward versus outward crushes it, right? All of the one orientation are pointing outward. All of the other orientation are pointing inward. This is extremely unambiguous. That's super. Okay, but in this case, you can't use upward versus downward. Right, so let's take, for example, the outward orientation here. This outward orientation, let me just get them highlighted here. If I try to call them upward, well, some of those vectors are upward, but these vectors down here are not upward. So that's just not a good description of this orientation. And furthermore, arguably worse, the other orientation, some of those other orientation vectors are also upward. Right, so this is pretty ambiguous. Upward versus downward doesn't mean anything. It does not remove the ambiguity. So that would be very bad choice of language. Right, so big X. Don't use that language for this surface. So anyway, that's how it works. It's, you gotta make reasonable choices. So for example, for this surface here, obviously you're not going to say upward versus downward. That doesn't mean anything. right? Inward versus outward, kind of okay. What I do like and what I think is the best option here is to notice that on this surface, all of one of the options, all of these vectors here, they all point in the negative y direction. Somewhat, again, not exactly, but at least somewhat, and that unambiguously describes this green orientation. And furthermore, the alternative, you could call positive y direction. Neither of these orientations is unambiguously described by their appropriate choice of words over here. Okay. All right. So think about the language. Right. So moving along. Questions? How are we doing? Is everybody happy with that? Okay. Okay. Sometimes you get lucky. These are nice opportunities. I'll remind you that in my undergraduate physics days, I did have to compute a ton of flux integrals. Flux is a big deal in physics. If you haven't taken a E&M class yet, you'll see when you take an E&M class, flux is a huge deal, right? And not only for E&M, let the record show. If you can compute such things by shortcuts, it's a really convenient thing to be able to do. It's kind of like with symmetry, different, of course. Again, my estimate is about 20% of the integrals that I encountered in my undergraduate physics major were zero by symmetry. I figure about 20%, ballpark. Right? So I don't know exactly how many of these kind of orientation good fortune integrals I got to take advantage of, but it's in the same ballpark. Maybe it was only 10%, but again, still really, really useful. So, for example, let's suppose you're interested in a sphere. By the way, it comes up a lot in physics and in engineering. Right, this is very, very real world for those contexts. And here's a vector field, and you want to compute a flux. And again, this comes up a lot. You want to compute fluxes through spheres all the time. Okay, well, here's the thing. I could parameterize the sphere, get a bunch of trig on the page, write it all down with trig, and deal with it with trig. And it'll go through and it'll get you the right answer, but there's just a lot of trig is going to show up. The slick move here is to take advantage of the fact that this is a sphere. And I encourage you to, heads up whenever you see a highly symmetric thing, right? So obviously you're going to look for symmetry opportunities when you see spheres, but also if you're looking at a flux integral, you want to look for geometry opportunities, and specifically that unit normal vector, the orientation unit normal, by the way, oriented outward, right? That orientation unit normal, because spheres are awesome, is a scalar multiple of the position vector. Right? Gotta love spheres. Spheres centered at the origin, to be fair. So, scalar multiple of the position vector. The position vector being x, y, z. So that is just my normal vector is just x over 3. And the vector field was given. Let's see here at the vector field. Let's pop that in there. And so again, before I parameterize, before I get invested with a bunch of trig, which, I guess that's how you have to do it very often. But by just kind of, let's scope this out. Let's see what happens. How can I take advantage of this wonderful symmetry that comes from the sphere? And what you get is a very easy opportunity to notice that this dot product is 0 and we are done. Right? And it comes about by, looking, hey, did I get lucky? Right? And so something to think about when you have nice opportunities, nicely symmetric things like spheres. Check it out. Who knows? Maybe this problem's a lot easier than you thought it was, and you don't have to, plug and chug and plow through tough ground. Yes?
Is that small n always equal to x divided by 3?
Always is a dangerous word for mathematicians, right? So it is in this case that we have a sphere centered at the origin radius 3, right? What I can say is that when you have a sphere, that's important. It's got to be a sphere. The normal vectors are always orthogonal to radii, right? It's because it's centered at the origin that the radius happens to also be the position vector. Does that make sense? Yeah. So, detailed doubles always matter. Yeah. Great question. Anybody else? Everybody's happy? Okay. Oh, you know what? I am going to insert a comment here. I don't have this written down, but I think it's probably worth noting. Y'all know I'm a huge fan of symmetry theorems. Right? Double integrals, look for symmetry. Triple integrals, look for symmetry. Do you have symmetry theorems for line integrals and flux integrals, surface integrals? And the answer is, no, it depends. So for scalar line integrals and scalar surface integrals, yes. I really should write, I'm realizing now I need to put a note about this in the notes. So expect an updated, and I know I updated them just yesterday, but another update, I'll say very soon, maybe tomorrow. But scalar line integrals, scalar surface integrals, yes, there are odd symmetry theorems. They're exactly what you think they are. They're totally analogous to double integral and triple integral symmetry theorems, odd symmetry theorems. For vector line integrals, it just doesn't work. And likewise for vector surface integrals, odd symmetry, it just doesn't work. And it has to do with the fact that the normal vector points in a different direction. The normal vectors are not they're not odd, you might say, and they're not even. They're sort of neither. The normal, if you were to reflect through that line, the normal vector over here, it's not equal to the other normal vector. It's also not the negative of them. It's just different, and it's different in a weird way. And so on flux integrals, odd symmetry is not something that you can entertain. Okay, so anyway, heads up about that. Notes to come. Okay, how are we doing? Everybody all right? Okay. Yeah. Here's another example where you get lucky. So, I've got a description here of my surface. And my surface, I can talk about, I want to talk about the flux of this vector field through that surface. How do I compute the flux? And again, you can parameterize and plug and chug, and that's fine. But you can also look for easy opportunities for wins. So there's two really nice things about this surface. First thing I'm going to point out, this surface, although there's a complicated story over here involving this inequality, it's part of this plane, y equals 3. So, oh boy, a bunch of complications involving quartics. Yeah. But it's all sitting inside of a nice flat plane perpendicular to a coordinate axis. That's pretty sweet. Okay. So that tells us a couple of things. On the one hand, it tells us exactly what my normal vector is. Again, I can just write down that unit normal vector. This is the given, right? Notice it says oriented in the positive y direction. So I know that the orientation vector is going that way, not this way. And again, gotta love that plane. Normal vector is obviously just 0, 1, 0. Okay. So that's nice. I'll write that down immediately. Here's the other nice thing about it being part of the plane y equals 3. The fact that y is equal to 3 plugs in very nicely into this formula, and this expression here, namely the second coordinate of the vector field, everywhere on the surface that I'm actually interested in y is equal to 3, and so therefore this term is straight up 0. And so I get a 0 right there. Everybody follow that part? So again, we're done, right? I mean, yeah, sure. There's a lot that remains yet to be understood about the surface. Yeah, there's a quartic inequality there, and oh my gosh, what's going? Doesn't matter though, because on that complicated surface, I'm adding up a bunch of zeros, and zeros always add up to 0. So again, walk away. You don't have to deal with all the ugliness. And this is another thing that comes up surprisingly often, and not just in manufactured, Math 219 questions, but in the real world, right? Obviously it doesn't come up at the grocery store, but as engineers, physicists, etc., this kind of thing, this is not rare. Okay. All right, is everybody good? Okay, so another notation thing. Y'all remember we talked about coordinate line integrals, and it came out of an observation that you can kind of rewrite what the dx vector is in coordinates. And you can just write things out in coordinates, and you get these kind of weird-looking, not very convenient in most cases, but weird-looking alternative notation for vector line integrals involving dx, dy, and dz. Well, here's a similar thing for surface integrals. Now, long back, we observed that this cross product, capital N, you could write out that cross product in coordinates, and when you actually cross it out, the coordinates of the cross product ended up all being little 2x2 Jacobian determinants. And I remarked at the time that, that's weird. But wasn't clear what we were going to do with that or why that was useful. So the use is going to come up now that we're interested in the ds vector. The ds vector being that capital N times ds dt, which gives us then this extra factor here, ds dt, and now multiplying that all out, right? Look what we have in these individual coordinates. For example, here, partial yz, partial st, ds dt. Again, it's as if these cancel, and again, they don't, that's not real. And I get the willies every time I do something like that. This is not real. That's not actually cancellation. After all, this here is not actually a fraction, right? But this is something that in the past we have rewritten as dy dz. For different reasons. We were talking about change of variables and etc. Yep. So we've rewritten that before as dy dz. And then likewise, wouldn't it make sense to call that dz dx? And likewise, you'd expect to rename this dx dy. Now, is there a natural geometric does this make sense in any natural, meaningful way, or is this notational games? It turns out, yes, this is actually very natural geometrically. Sadly, it's very natural geometrically in a way that takes about 15 minutes to explain in class. So I'm not going to go through the geometric interpretation of why this makes loads of sense. I'm just going to claim that this makes loads of sense. If you're curious, if you're interested, and if you got 15 minutes to spare, come on into my office hours. I'll be thrilled to go through and talk about what this looks like geometrically and why it's actually really natural. But you're not responsible for it, so you don't need to worry about it. The punchline, though, is that what we have now is an alternative coordinate notation for our ds vector. Right, so ds is that thing, and so plugging that in to a flux integral, and let's not forget that our vector field is going to have coordinates. Let's call them PQR. Then, crank out that dot product, and that dot product is just that, and this is what we call a coordinate surface integral notation. So again, this is an alternative to the usual, I might call this a vector notation for a flux integral. This is what I would call a coordinate notation for a flux integral. So they're the same per this connection here, but look very different. Everybody with me? You can probably guess what I'm going to say next, and that is I have a preference between these. Right? In the context of Math 219, I think this one makes by far the most sense. It's the most relatable. It's the most compact. And, well, that's a pretty strong case right there. Right? So I'm going to heavily lean toward this notation right here. Just be aware that this notation is out there, and now in defense of this notation that we're not going to have, honestly, all that much use for in Math 219, let me tell you why people like it and why people are very reasonable to like it. If you write down differential forms, and again, take a glance if you're curious at Chapter 8, that's what differential forms look like. Yeah, they actually look a lot like this. Not exactly. They look a lot like this. And it's powerful stuff, right? Differential forms allow you to do things that we just can't do without differential forms. It's extremely powerful mathematically. And again, I'm going to make the claim, and again, I'm not going to tell you what differential forms are exactly, but it's also ultimately very natural. But all this differential form stuff is well beyond Math 219. So, you can have to take my word for it, but that's why people like this notation. And therefore that's why this notation's in common use. This notation here, because it's in common use, that's why you need to know it. Right? This is you're gonna see this. Right? And my advice is that when you see a surface integral, integral over a surface, and then function, and then coordinate differentials dy dz, pretty weird. If you think about it, right? This dy dz is not telling you about the area of a piece of surface or anything like that. It's almost it looks like a mismatch in a way. But when you see this, just keep in mind this is this kind of this very different notation for what is in fact just a regular old flux integral. Right? Okay. All right. Questions? Everybody all right with that? All right. Okay, so again, now I'm going to bring up differential forms again, not because we're going to study them, but I'm going to make a cultural note, and I think this kind of thing is healthy to know, because differential forms are a thing, and ultimately, very natural, etc. It's useful to know that in fact, line integrals and surface integrals are both actually examples of those things. I mean, we don't think of them that way, and we're not going to compute anything involving them in that way, but the reason it's useful to know that line integrals are integrals of differential forms and surface integrals are integrals of differential forms is because that suggests you can kind of see, well, if these are just two examples of the same thing, maybe there's actually connections between them. Connections between line integrals and surface integrals. Kind of plausible. I mean, minus this discussion of differential forms, it would seem baseless to see it. I mean, line integrals and surface integrals come up in totally different contexts. One is on a curve, the other is on a surface. They're different. One's about flux. One's about circulation. Right? I mean, they're very different things. Why would there be any reason to think there should be any connection between them? The fact that they are both ultimately coming from the same place suggests that maybe there should be some connections here. And ultimately, that's why these connections that I'm about to show you, these analogies that I'm about to show you, why they exist. This is not a coincidence. What I'm about to show you. This is ultimately because we're talking about ultimately kind of the same things. So, okay, here's the analogies. Now, the way I wrote this down, I've got to squeeze it all onto a page, right? And so I had to kind of compress. Normally when we draw a parameterization, we do it to the left to right, but there's not enough width on the page for me to be able to, I wanted to be able to have line integrals on the left and surface integrals on the right so that we can kind of compare and contrast. So apologies for the parameterizations being kind of, at a diagonal like that. But okay, so in both cases, we have a parameterization. In both cases, we talk about the derivative of the parameterization. Remember, velocity is the derivative of the parameterization when you're talking about a curve. Well, capital N, it's not exactly the derivative, but I mean, it's very derivative related. How does capital N come up? What's the formula for it? Well, it's a cross product of the partial derivatives, right? It comes from derivatives. So the velocity vector here, the capital N vector here, kind of analogous in that sense, in a way. Different, of course, appropriate to the context. Okay, in both cases, we talk about, let's see here, we talk about a unit vector pointing in the direction of that derivative. And that these unit vectors define what we call the orientation. That's a coincidence. In both cases, we talk about a vector, the dx vector on the left, the ds vector on the right. Right? These being vectors that point in that same direction and whose magnitudes give you the size. So again, another analogous thing, we have this notion of size of a little piece of curve and a notion of size of a little piece of surface. Right? So I like to use colors to just draw attention to the analogies. Notice how the color layout on the left, color layout on the right is pretty much the same. Right? And all of this extends pretty naturally to when you start writing down equations. So let's see here. So we've got this dx vector, right? Here's the ds vector. And then let's see here. We have ds scalar there and there. D capital S scalar there and there. Let's see here. We have the unit tangent vector there, the unit normal vector there. Again, notice how the layout is exactly analogous. Right? Let's see here. We have the velocity vectors and the derivative of the surface parameterization, the capital N vector. So the analogy is extremely strong. And I just think that's worth pointing out that, again, geometrically we think of surface integrals as being, well, it's totally different geometry than line integrals. And yeah, true. It is totally different, but it's shocking how similar the algebra is. Oh, I can include on here pullback differentials, right? dt is the pullback differential on the left, ds dt, pullback differential on the right. The pattern is just overwhelming. Everybody see what I mean? So why do you need to care about this? Well, for one thing, I mean, I think this is good cultural. I mean, it's nice to realize, even if you don't have to know why or be able to prove that these things, that this analogy is what it is, it's still nice to know that it's there, right? Just be an awareness of what's out there. By the way, all this discussion here is not in the book. This is just a supplemental thing that I think is really useful. For whatever it's worth, I also think that this can be really helpful as a learning tool. So, a lot of students, for example, find themselves uncomfortable with, what's the deal with the capital N vector? right? What is that, and how should I think about it? And I think a great way to think about the capital N vector is to realize, look, it's the surface integral version, the surface integral analog of the velocity vector. It's a derivative. It's the thing whose direction defines the orientation of the parameterization. It's the thing that you multiply by the pullback differential to get your vector differential. Both sides. Right? So that analogy might help you sort of make it easier to keep track, if nothing else, of the roles that capital N plays and how to think about it. So there's that. And I am not going to continue the analogy coloring in, fun though it is, down here. But if you were to keep coloring, you'll notice down here with our various formulas for work integrals, various formulas for flux integrals, the analogy continues in all these formulas as well. So, okay, good place to draw the line. We did finish section 7.2. I will have to wait and see how we do in the afternoon lecture as to whether I'll assign it for this week's homework. I'm optimistic. So, hopefully. But anyway, y'all have a good day. See you later. Don't forget to stick around for attendance if I didn't already get you.